Jai Hind to all. We are here to again continue on data analytics. It is CS051. We are on the unit 3rd, and which is talking about mining data stream. So there are various concepts related to streaming of data that we want to put up over here. How it is different from our stored data. Since we are talking about streaming of data, so it is something like this, that a stream whole big data in various velocity, volume, veracity, all V's, 5 V's that we have earlier talked about. They all come in this high frequency and high velocity and high volume, high variety, and they need to be analyzed. So the challenge is storage, the challenge is its speed, and challenge is its analysis. So streaming data, no doubt, different from stored data that we have been talking about, our DBMS, wherein we have our data stored in our well-structured databases. Opposite to that, we have streaming data where there is no structure, there is no SQL involved, and there is fast-flowing data coming in. So it is something like this stream of data that is flowing through, and we have to analyze this. So streaming data refers to the data that is continuously generated, usually in high volume and high velocity. Good enough. A stream that would typically consist of stream of logs that records events as they happen. So what we have to focus is on finding, analyzing on the streaming data, and for that we need to have certain algorithms, certain techniques to handle this streaming data. So such events such as user clicking on a link in a web page or a sensor reporting the current temperature, these are all example of streaming data, and we need to analyze this. So common example of streaming data would be IoT sensors that are throwing data every seconds, server and security logs, real-time advertising, or click streaming data from apps and websites. These are altogether different from traditional databases like library management system, hospital management system, where the database is more or less stable. Only the transactions are different. Yeah, over here we have different data. We have different transactions, we have different algorithms altogether to handle the stream data. This is again the same input data in various velocity, variety streaming into and being observed, being analyzed. Same thing in a different pipeline. We have text data from various sources streaming through various architectures, like Kafka architecture is common architecture to collect streaming data. Then for processing, we have Spark, we have Hadoop ecosystem is having altogether various support system for processing, collecting, storing all this streaming data. Then we apply machine learning algorithms at this processing level. Then we store it no doubt, not in our traditional databases, but in a NoSQL databases, like we may need map, we may need NoSQL databases, JSON, or we may need columnar databases. All those are unstructured databases that we are talking about. And then finally, analysis is done through these tools, such as we have Apache Drill, Spark SQL, various databases analysis tools are also there. So challenges of streaming data is it is not processed immediately or stored, then it is lost. If we are not able to process it immediately, then the data is lost forever. That is opposite to conventional data, where data is stored and we can analyze it at our own speed. Then second, unbounded sequence of data is there. It may not be related to or correlated with each other. That is opposite to RDBMS, which is there is a relation among various data sets. There is no correlation within this data set. So traditional processing, wherein we are storing the data and posing a query on that. So we have historical facts finding. These type of data handling is there through a traditional processing system. Hierarchical fact finding, find and analyze information stored on disk. Batch paradigm pull model is there, and then query driven submit queries are there. Opposite to this is streaming data, where we have current fact findings, analyze data in motion before it is stored. Low latency paradigm, push model is there, opposite to the pull model over there, and then data driven brings data to a analytics. So traditional data processing versus streaming data processing is basically differing in the time interval that they get to analyze. the window that is there, only a short window that is there, within that the analysis has to be done, and there is no basically storage of data. It is on the flowing data that analysis is done. And under the streaming model, data is fed into analytics tool piece by piece, and the processing is usually done in the real time. So batch versus streaming data. Use case for batch processing can be payroll, billing, order from customers, and use case for stream processing could be fraud detection, social media sentiment analysis, log monitoring, and analyzing customer behavior. These are the various application area of streaming data. As opposite to batch data, that traditional data bases we have been talking about. Then streaming data architecture. Streaming data architecture is an information technology framework that puts focus on processing data in motion and treats extraction, transformation, and loading batch processing as just one or more event in the continuous streaming of event. So when the continuous streaming of event is happening, ETL is one of the phase wherein we are extracting, transforming, and loading the data, right? And then loading again needs, if the different type of data is coming in, we need to extract it and transform it in one format and then load it at the other end. So big data architecture and pattern, it is talking about layered performs a particular function. Each, it is just basically having a big data solution is there in terms of Hadoop ecosystem, and there is layered architecture wherein each layer is giving one functionality for it. One may be giving for storage, another may be for processing, another may be for analysis, all that. So this architecture helps in designing data pipeline with various requirements of the batch processing system and stream processing system. This architecture consists of 6 layers which we ensure secure flow of data. What are these 6 layers that we talk about? First, you inject the data in your databases. No doubt you get data from various sources of data, such as maybe from internet, from stored reports, from unstructured, structured files, from maybe from Twitter data, maybe even RDBMS data. So various sources, sensors data, the various sources of data are there. That is 0th level that I am talking about. Then we have data ingestion layer, wherein all the sources of data, data from various sources are injected into the system, and then data is collected, stored, processing layer is there, then data query and data visualization. These are various steps, steps or steps behind this architecture of data processing. These are various data sources. They are the Twitter data, then we have our LinkedIn data, or even stored data, or even reports, all those blogs. Various sources of data are being, data from various sources are collected, injected, and finally various storage, processing, layering activities there, analysis is there. At this part we have statistical analysis, semantic, predictive text analysis is happening, and finally the visualization of the data to be able to explain the data or maybe explain the pattern within the data to the end user. So data visualization layer becomes the last layer for whole data analytics process. So various data sources that we have talked about, it can be from e-commerce sites, it can be from IoT devices, sensors. Then second, then we have ingestion of data, storage, processing, query, and then visualization. So data ingestion layer consists of variables, various tools are there for data ingestion. Apache gives lot of utility in data streaming ecosystem. Apache Flume and Apache Nifi are the one who are giving us the facility to inject the data into the system. Then Kafka, Apache is only, Kafka architecture is there, that is supporting for data collection. Then we have data for data processing also, where there is a lot of tools given by Storm, Scoop, Flinks, again Apache, Spark. So Apache is a rich source of, various utilities available for data processing or streaming, handling data, streaming data. Then data storage layer, we have Hadoop, then Gluster, Amazon S3 is there. Then we have for data query again, we have Spark, we have Presto by various vendors. Then for data visualization, we have Kibana. These are various tools available for data visualization. Tableau is the most popular in industry. Kibana is another more popular. Angular JS, React JS, these are the ones which are used for data visualization phases. These are the tools available for commercially available for data visualization. Herein, I would like to explain one small subtopic, that is client server architecture as against publisher and subscriber architecture. This would be required because it is part of Apache Kafka architecture that talks about how the services are being shared. So, if it is a client server architecture, over here I would like to differentiate between these two architecture. Client server architecture, there is a client who is requesting for a service and the response is being given by the server directly, as opposite to the new architecture that is available in Kafka, Apache Kafka, that is talking about not having direct relation between client and server. Directly response and request relation is not there. Instead, there is an interface between the two. There are a set of publishers as opposite to servers. There are set of publishers and there are set of subscribers. Publishers are the one who are going to request certain services, and the subscribers are the one who are going to give certain set of services. They are going to request and they are going to subscribe, or they are going to give the response. So, instead of giving the response and request directly like in client server, here there is an architecture that talks about a service model. Beach mein there in the center there is a interface that becomes an interface between publisher and subscriber in the form of these are the common points. Publisher publishes all the services to this publisher point, and then subscriber gives all its services on the subscribe nodes, subscribe, unsubscribe, whatever various functions they are giving through this interface only. So, publisher whatever request they have to do, they do it through this publisher request through the interface, and that is served by subscriber, not directly. Instead, they are doing it through the subscriber or unsubscriber, or this interface is there to subscribe the services. So, publisher subscriber messaging or pub sub messaging is a form of asynchronous service to service communication used in serviceless and microservices architecture, as opposite to synchronous architecture that we have in the traditional client server architecture. In pub sub model, any message publishing to a topic is immediately received by all other subscribers to the topic. So, here these services are available for all the publishers, and whatever various publishers are publishing or requesting the services for, it is available and visible for all the subscribers, as opposite to the earlier one. Another, there is a Lambda and Kappa architecture that is very popular when you are discussing data processing architectures, and there is a point of difference of Lambda and Kappa architecture is in terms of maintaining this point. Real time layer is there. So, in Lambda architecture we have incoming data, we have batch layer, we have servicing layer, we have real time layer, and then data is already there. This real time layer and servicing layer is there, history, data storage and result storage is there. What is missing is this batch layer. So, what we can see in Lambda and Kappa architecture, how does it differentiate? Basically, these are both are data processing architecture that we have, that is part of the 6 layers. So, Lambda and Kappa is evolving architecture, wherein in Lambda we have batch layer as well. So, there is a batch processing possible along with real time processing and service layer, all those. But in Kappa architecture, this batch processing part is missing. We just have real time layer, the servicing layer, and then the storage layer, and that is also very temporary storage is there. Very limited storage is available, a very temporary storage is available when we talk about streaming data. So, where is the point of difference? No doubt the batch layer. So, Lambda supports both real time and batch processing as well, whereas Kappa architecture only supports real time processing. So, that was batch and stream processing that we have talked about. This is again detailed streaming model, wherein we have input stream, then ad hoc queries are posed on that input streaming data, Then limited working space, as I have talked, that we have very limited storage available in a streaming data, and some ad hoc queries can always be placed on that streaming data and giving some output. So stream model may be achieved in a large archival storage, and there is also working storage and summaries are there. A working storage might be disk or it might be a main memory, and depending on how fast we need to process the queries, but either way it is a sufficiently limited capacity. This is the key point. We have a very limited storage in our streaming data because we cannot afford to store all the data and store it and then process it. All the processing is happening in a real time fashion. So these are the same key points. In analogous to database management system, we view a streaming processor as a kind of stream data management system. So let's move towards more detail. In many data mining situations, we do not know the entire data set in advance. That is there, and that is why we say that we are handling streaming data. We are handling data which is infinite and which is non-stationary. So what are the streaming data sources? Google queries, Twitter or Facebook status updates. These are all streaming data, for example. Then we have input elements can enter at a rapid stream. We call elements of the stream as a tuples. How this term tuple has been used over here as opposite to RDBMS, where data is stored in a well tabulated data and each row is called tuple. Here the same word is being used, but in streaming model an element enters at a rapid rate at one or more input ports, and these streams, we call these elements of the stream, is called tuple. So as opposite to one row in our data RDBMS system, whole a stream of data is called tuple over here. In this case, system cannot store the entire stream accessibly, that we have already talked about. So problems on data streaming, types of queries one wants an answer to is how to sample data from a stream. So when we have streaming data, how to handle that, so since we cannot fetch the whole data, we do sampling. Then there can be certain issues related to sampling, whether we are replaceable or the sample is replaceable or not. So various sampling issues comes into play. So since we cannot handle the whole streaming data, we manage with the sample, and now the issues related to sampling may appear in this case. So the types of queries one want to answer on a data stream is how to sample data from a stream. So this becomes a key point. How do we sample the data? How do we construct a random sample? Then queries over sliding windows. Number of items of type X in the last k elements of the stream. So this type of query will be formed. What are the different types of elements available in last k streams? Means since we cannot handle the whole data at a time, so we are talking about sliding window. Means part by part. In this, suppose we are talking about this part of the whole streaming data is there. We are only talking about this part of the stream, and all the queries are being put up at this part of the stream only. So this is sliding window concept which is there in a streaming data. So what are the issues? One is when we form this window, how efficiently this window represents the whole stream, because again there is an issue of sampling, whether this part of the window is able to represent the whole stream or not, right? Maybe there is scarcity of data in this part and maybe it is denser ahead. So the sampling issue will be there, and that is there in a streaming data, that there is a issue related to sampling and how good this sliding window is, because how good this sliding window is representing the whole of the data. So that is the issue. What are other issues? Types of queries one wants to answer on the data stream is filtering data stream. Select elements with property X from the streaming data. Then counting distinct elements. These are various problems on data streaming that may happen. Or you can say standing queries that we have talked about that can happen. So what are these standing queries that can happen on a streaming data? Counting distinct element, number of distinct elements in the last k elements of the stream. So these only we can find it out. Instead of finding out what is, since we are talking on a streaming data, so number of distinct element in k elements of a stream. So if this is the sliding window that we are talking about, so how many distinct elements are available in this part of the stream only? We cannot handle whole of the data. So that window, within that window, how many distinct elements are there? So these are various types of query that we can talk about in a streaming data as opposite to RDBMS. Then estimating moments, estimating average, standard deviation of last k elements. So these are various queries that can be found. Then finding frequent elements. So what are queries that we can query at a streaming data is counting distinct element, what is the average standard deviation, what is the frequency of each element. Then mining query streams. Google wants to know, suppose this type of query is there, Google wants to know what queries are more frequent today than yesterday. So for that you need to have the latest data with you. We cannot manage with the stored data, and we want to know what is the most frequent query today than compared to yesterday. So such queries can be part of your streaming data. Then mining click streams. Yahoo wants to know which of its pages are getting an unusual number of hits in the past hours. So within an hour, what changes has been there, what play has been made with the streaming data, that one wants to know. So these type of queries are there with the streaming data. Mining social networks, news feeds. Then looking for trending topics on a Twitter, Facebook, maybe within an hour what topic is trending. So these are various application area of streaming data. Then sensor networks, many sensors feeding into a central controller. Then telephone call records, data feed into customer bills as well as settlements between telephone companies. So these are application area of streaming data. Then IP packets monitoring at a switch, gathering information for optimal routing or detecting denial of service attacks. These are various application area for streaming data. Streaming architecture, publisher and subscriber, we have already talked about. So considerations and approaches to this. Managing stream data, again the same. Various ways in which we can manage stream data is sampling. So what are the management that we have to do with the streaming data is manage stream data. We should look at the extracting reliable samples from the stream. So as I have already talked, sampling is an important concern. What part of the data should be sampled, how much it should be sampled, what should be the sample size which is representing whole of the streaming data. So these are concerns that we have to look into. So another common processes on stream is selecting or filtering. Filtering to find how many zeros are there, how many ones are there, or how many new users have come in, what is the trending topic, how do we know about, unless we filter that data. So the second concern will be filtering. We want to accept those tuples in the stream that meets a criteria. Since we are filtering, we need certain criteria over which that filtering has to be done. So what is tuple? We have talked about is the streaming data, and within that we have to find the criteria. So accepting tuples are passed on to another process as a stream while other tuples are dropped. So what do we need? We need Bloom filtering. I will discuss Bloom filtering, counting distinct element, Flagellate-Martin algorithms. All these are algorithms with a numerical in detail in our upcoming classes. But as of now, let us see what are the various algorithms or what are the various issues that we may face while handling streaming data. So one is how to sample, how well we are sampling. Then filtering, how do we filter? Using Bloom filter, we can filter the stream of data to find certain criteria. Maybe we want to find what is the number of new users in this span of period time, or maybe how many how many clicks have been done in this span of time. So for that, certain filtering has to be done. So that is handled using Bloom filtering. Then, or we are checking whether some new elements has come in or new users have come in. So all that is done using Bloom filtering. Algorithm behind that is filtering is Bloom filtering. Third simple kind of processing we might want to do on a streaming is counting distinct distinct elements. The Flagellate-Martin algorithm, FM algorithm, is a very popular algorithm used for counting distinct elements. We will do numerical based on this also, and this also in our upcoming classes. Then we want to find estimating moments. What generalization of the problem of counting distinct elements in a stream? The problem called computing moments involves the distribution of frequencies of different elements in a stream. So Alan Matters sets algorithm for second moment. So what does this moment analysis gives us? how well is the distribution of various element in this frequency. So it is just checking, are we getting all zeros over here till this frame only and then getting all ones in this frame, or we are getting zeros and equally distributed within this frame. So how well our data is distributed along the stream, all that needs estimating moments. So AMS algorithm is very popular algorithm for finding the distribution of the elements within the stream. These all algorithms have appeared from statistical methods. Whether we talk about moments or we talk about AMS algorithm, the basis behind this is statistics only. So basically somewhere data analysis and probability and statistics is connected and well connected. That is why all the algorithms that appear in these literature are coming from either probability or statistics or maths, broadly speaking. Then counting ones in a window. So we need their situation when we want to find number of ones in a window. Within this window slide, how many zeros are there, how many ones are there, so that they may tell us about the change or maybe the count. So counting ones in a window, Data Analytic Lecture algorithm, DIGIM algorithm is a popular algorithm that is being used to count ones in a window. And then decaying window, finding the most popular elements. Trending, what is trending? So suppose we want to find what is trending within 1 hour, which topic is trending within 1 hour, or which advertisement is being clicked most. So the way of finding popular elements and trending elements is finding the decaying window. So we have various numericals based on these topics that we will be handling in our next classes. So let's start with the sampling, the first part. Managing streaming data, we shall look at extracting reliable samples from the stream. So let's talk about sampling first. After that, we'll talk about Bloom filtering. Then we'll talk about Flagelet-Martin, and then AMS, and then DIGIM algorithm. So sampling, general problem we shall address is selecting a subset of a stream so that we can ask queries about selected subset and have the answers be statistically representative of the stream as a whole. What fraction of the typical user's query were represented over the past months? Were repeated over the past. Assume also that we wish to store only 1/10 of the stream of the element. Now, what the challenge is with the streaming? Suppose we have certain query, what are the new users query? What fraction of typical users query were repeated over the past months? Up now, and we assume that we wish to store only 1/10 of the stream. First of all, since we cannot store whole of the stream, we'll have to keep a sample of it, and the sample is suppose that we maintain 1/10 of the data we will store as a stream. Now, and within that 1/10 of the data that we want to see, what is the query repetition? Now, so there is lot of other factors involved. How well the data is distributed, that whenever you are taking 1/10 of the data, it is representative of the whole of the data set. So sampling has its problem. It's difficult to say which part of the sample is representing whole of the data. So suppose we only keep 1/10 of the stream for sample, but how does it differ if we keep it 1/20th or we keep 1/30th of the sample? So these are the points where we can play with the sampling of the data. So how well that sample is representing the whole of the stream is a maybe it's a research concern. So what fraction of the typical user's query were repeated over the past months? This is the type of query. Then sampling, suppose we choose of 1/10, then how well that sample is representing whole of the query, whole of the stream is a concern that we have to look after. However, this scheme gives us wrong answers to the query asking for the average number of duplicate queries for users. A reservoir sampling would be required for that. So various types of sampling is there. Sampling from a data sample, sampling a fixed proportion like that we talked about in this case, 1/10 of the streaming of the data that we have talked about. So we have fixed it as fraction to be 1/10. As the stream grows, the sample also gets bigger. So what is the problem with maintaining this type of sampling that we want to keep 1/10 of the stream of the element. So as the sample, as the stream grows, so maintaining 1/10 may increase the sample size as well. So we have to again handle that also. As the stream grows, the sample also gets bigger, because we have talked 1/10. How much is 1/10 will again depend upon the volume of the data. If the volume of data is high, 1/10 will be very huge amount that has to be stored, and if it is low, then it can be managed. So that is the concern. So sampling from a data stream, since we cannot store the entire sample, an obvious approach is to do sampling. So what are the different types of sampling that we have? Sample a fixed proportion of element in the stream, as we talked, say 1/10. Then, or we may have a random sample of fixed size. Means, instead of maintaining 1/10 of the data, we just take the, out of the streaming data, we just say take some random samples, maybe some from here, some from here. So maintaining random sample can be another approach, because fixed proportion data, fixed proportion sampling led to the problem that if the say data stream size is increasing, even sample size would be increased, and so its problems related to its storage analysis will come into play. So what do? We maintain a random sample of fixed size, right? So we either we fix the size of the sample, or we fix the proportion. So if we fix the proportion, the issue was increase in volume with increase in data volume, and random sample of fixed size can be another approach. So maintaining a random sample of fixed size over a potentially infinite stream. So this is an infinite stream, and we have said that we will keep only x byte of data. So that is a sample of a fixed stream kind of. So at any time k would be like a random sample of S elements. What is the property of the sample we want to maintain? For all the time step k, each of the case elements seen so far has equal probability of being sampled. So if we are putting sample size as fixed one, so how good that that approach will do the sampling very well. That is the concern. Then we have reservoir sampling. Reservoir sampling is a family of randomized algorithm for choosing a simple random sample without replacement of k. So reservoir sampling can be with replacement or without replacement of the k elements. So without replacement of k items from a population of unknown size n in a single pass over the item. Size of the population n is not known to the algorithm and is typically too large to fit all n items into the main memory. So this approach of whether we are sampling with replacement or without replacement, they have their own challenges. So in summary, we can talk about sampling a fixed proportion of stream can be one approach. Sample size grows as the so what is the disadvantage of it? The sample size grows as the stream grows. Second approach can be sampling a fixed size. So the reservoir sampling can be approach to the same. Then we are talking about the second issue. If we move back from this slide, filtering. Sampling is done, wherein we talked about reservoir sampling or sampling of a fixed size, or then we talked about second concern, and that is filtering. When do we need filtering? When we want to know certain items, how frequently those items have been there in the stream and all. So such queries needs filtering. So for that we have Bloom filtering. So we'll start with Bloom filtering from here. Yeah, this is the concept of Bloom filtering. This is the second topic that we have to handle today. So Bloom filtering is a data structure designed to tell you rapidly and memory efficiently whether an element is present in a set. And the price paid for this efficiency is that Bloom filter is a probabilistic data structure. It tells us that the element either definitely is not in the set or may be in the set. So what is the purpose of Bloom filter? Basically, if we see, Bloom filter is something like this, wherein we are checking these X elements are there in this Bloom filter or not. If it is there, we say yes, it is. If and with what probability that element is there in that Bloom filter. So it's a data structure that is designed to tell you rapidly and memory efficiently whether an element is present in set or not. So, this is very ideal for handling data when it is a streaming data. So, the price paid for this efficiency is that Bloom filter is a probabilistic data structure, right. So, it may have its own concerns related to probability, whether it is a false or false positive or false negative, all these concerns are there. It tells us that the element is either definitely is not in the set or may be in the set. So, it only gives a result in two form, either it can be negative, but it is we are sure that the element is not present, or it may be present. So, maybe or sure that it is not present. So, it can be either negative, that we are sure that the element is not present, or it may or may not be present. So, these are the two states that we get out of this Bloom filter. How do we go about it? So, how do you filter out an email IDs as good one and a spam? Suppose we want to do this classification, this filtering, whether this email ID is spam or not. So, the typical email addresses is of 20 bytes. Strategy, if we have 1 GB memory, that is 8 billion bits, then map, what are the strategy behind? We should use hashing. Map hash of a good address to a built location. So, email hash to 8 billion memory addresses and mark 1 on a location of the hash. So, wherever the element is there, it is marked as 1 or else it is marked as 0. So, this is just the concept. We will handle this with a numerical and see how it is used. So, hash to memory address and check if it has 1 or a 0. So 0 and 1s gives us the idea whether the element is present or not. Assuming every large spam percentage, this will eliminate about 80% of the spam. So, no doubt this Bloom filtering is not 100% efficient, but 80% of the spams are being filtered by through this. So, it is a old concept of 1970s, which has been heavily used for filtering over here in our streaming data. So, false positive is the act of wrongly classifying spam or non-spam. So, as I told, the outcome of this filter can be either false positive or true positive or true negative. 4 combinations are there. So, the false positive is the act of wrongly classifying a spam as a non-spam. And in the example, using one hash function, false probability is 11.75, and using 2 hash function, probability is 4.89. So, getting false positive is obvious because it is in a probabilistic model, it is working on a probabilistic model. But again, we can reduce the probability of getting false positive by increasing the number of hash functions. If we increase the number of hash functions, our probability will increase. So, what is the intuition? This technique may also be used to count shopping cart that has set of items A, B, C, and then see which item is there and which is not there. So, what is the algorithm is? The flow chart is like this. A Bloom filter consists of an array of n bits, initially all zeros, then a collection of hash function h1 to hk. The more hash function we have, the more accuracy we may achieve, as we have shown over here. As in this case, we have seen that the false positive probability is higher when it is only one hash function. The more hash functions we have, the probability of getting false positive is lowering, right. But no doubt it will increase the computation cost as well. So, we are moving towards the concept, and after that we will have the algorithms, and we will do one numerical based on this. But before that, let me just go through the algorithms. What is that algorithm? The Bloom filter consists of an array of n bits, initially all zeros. Good enough. We first declare what is the array that will be required, and initially suppose it's array of A5 of size 5. So, we have 0, 1, 2, 3, 4. These are the size of the array. We start with an collection of hash function with array of n bits, where n we have taken it as 5. Initially all zeros. So, initially we assume that no element is there in this array. So, initially all zeros. A collection of hash function h1, h2, h3, hk. the more number of hash functions we have, the more accuracy we get. So, collection of hash functions h1 to hk, each hash function maps key values to n buckets corresponding to n bits of the bit array. So, we'll do this. How do we find this key value and how do we fill this arrays, and when do we say this array's value is going to be 0 or 1? We'll talk about it through a numerical. Then we have a set of S of m key values. The purpose of Bloom filter is to allow through all streams elements whose keys are in S, while rejecting most of the stream elements whose keys are not in S. So, if that element is there or not there, we'll be getting an output of this Bloom filter, whether that element is present there or not. So, while rejecting most of the streams elements whose keys are not in S. So, initialize the bit array and begin with all bits zeros. So, we start with all bits as zeros. Then each key value in S has S and hash is using each of the k hash function. Set to 1 each bit, that is hik for some hash functions hi and some key values k in S. To test a key that arrives in a stream, check that all h1 to h1, h2, hk are ones in the bit array. So, if all are ones, then let the stream element through, and if not, if one or more of these bits are 0. So, outcome will be, if any one of the value is 0, then k would not be in there and so reject the stream. How do we find whether we should accept that stream or reject that stream, or whether that element is present in the stream or not? That element is surely not present, as I have talked about it abhi. It will be negative. When it will be negative, either of those values will be zeros. If then it is negative, and if either of these values 0, then we get it is not present. We are sure that it is not present, or else we can say that it may or may not be present. Okay, that probability may be involved. So, let us see the one example for this. Check whether an element is present or not. So, there are two concepts, that is false positive, not sure of the presence, versus not false negative, that is sure not present. So, these are the outcomes that we get. We are sure that it is not present, this one, sure not present, or not sure of the presence, or we can say it may or may not be, present. But here we are sure that it is not present, that element is not present in that stream. So, what are the steps involved? Put the given value in hash function, apply hash function and put the array, fill in the array, apply the same hash function on new value to check its presence. If all pass the Bloom test, it's false positive. Even if one is missing Bloom test, it's not false positive. So, these are the conditions theoretically. Let's talk about it. X elements are there coming in, and through the Bloom filter, we are up. Yeah. So, we'll continue with the Bloom filter numerical in our next lecture, and that is all for now. Bloom filtering is a numerical topic that I'll continue in the next class. Thank you.